Good day, everybody. This is a video for my intro calc students. And what I was going to do in this video is a couple of the tougher questions. I've actually had 3 different people ask me to help them with these 2 particular questions from the homework. I've had some questions about other questions too. But I thought I'd pick these guys because they've come up a few times, and it's just nice to kind of watch and see the explanation as to how you kind of do some of the advanced algebra in this stuff. So I've picked a couple that, again, people have asked more than once about. One's number 4, and one is 6e. And 6e doesn't even look like the toughest one here in number 6, and it probably isn't. But I've had 3 different people frustrated by the fact that they thought they did 6e right, and they just don't get the same answer that the back of the book has. So I'm actually going to, I'll tackle that one first. So I'm going to go to 6e. So all that we have to do with 6e is differentiate this thing. And it doesn't look all that hard. Obviously, it's going to be a chain rule and a quotient rule put together. So as we usually see in these questions, the first step is to change this to a radical, or a radical exponent instead of, or sorry, let me say that again, a rational exponent instead of a radical. So it looks like that, 2x plus 3 to the power of a half. Now I can approach it with my quotient rule and my chain rule. So now I'm doing my derivative. So I have f prime of x. All right, so the chain rule says we take the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. And to do the derivative of this denominator, here's where I need chain rule. I could use a substitution and call this u, but I'm fairly comfortable with chain rule, so I'm just going to go right into it. So the chain rule says this exponent becomes the coefficient, and then you leave the bracket alone, and then subtract 1 from that exponent, making it negative a half. And then we times that by the derivative of what's actually inside the bracket, which would be 2. And finishing off quotient rule, it's the denominator squared. All right, so there we go. That's fairly straightforward. This 1 doesn't mean anything, so simplifying this a bit, I get 2x plus 3 to the 1/2. And this I can tidy up. I have a half times a 2, so those 2's can cancel. So I have minus x times 2x plus 3 to the negative 1/2 all over. And this is kind of nice. When you take the power of a power, of course, you multiply the exponents. So this ends up just being 2x plus 3. And I had some students who, the 2 of the 3 people asked about this question, kind of stopped here and then wondered why it didn't look at all like the solution in the text. Just to show you, the solution in the text is actually this. So as you can see, that doesn't look much like it. The only thing that looks kind of like it is that, well, you have a 2x plus 3 in the denominator, but it isn't even to the power of 1, it's to the power of 3 halves. And how on earth does the numerator become an x plus 3 instead of a 2x plus 3? And then I had people trying to factor out the 2 from these brackets, and then that doesn't work like that. So I'm actually going to show you a couple ways that you can turn this into this. You know, the first thing I do when I'm in this situation where it's like, okay, I have an answer, but the answer in the back doesn't look like my answer, is I will actually check to see if I just did the calculus right. Because I'm actually done my calculus, right? I've used quotient rule, I've used chain rule, calculus over. Now it's just algebra and arithmetic at this point. So did I do the calculus right? So I like going to Desmos and opening up Desmos and saying, okay, here's the original function. I'll graph it. You have to call it an f of x when you do that. And once I've graphed it, I can ask it for a graph of the derivative. So here's the derivative. It's this blue line. Let me get rid of the original function. There's the blue line. Now, here is what I just solved for. Here, I'll show you again. This is how far I've gotten, right? I typed in the powers of a half as 0.5s and negative 0.5, but it's still the same thing. So I've gotten to here. Is this the same line as what the computer calls the derivative? And look at that. Yes, it is, right? Green line, blue line. It's the same. Then I punched in what the back of the textbook says the answer is. Let me just show you again. I just used 3 over 2. I just put that in as 1.5 because it's less typing. But type that in. And now if my answer and this answer are the same, once again, it should be the same line. And it is. Purple line, green line, purple line, green line. So all 3 of these lines are the same. The computer's idea of what the derivative is the same as my idea, is the same as the textbook's idea. So I can rest assured, I can sleep soundly tonight. I've done the calculus right. But that begs the question, how do I make this look like this? So I'll actually do it 2 different ways. Doesn't really matter which way you approach it. I kind of like the first way. I'm going to do it better, so I'll do it first. I am going to factor. I know that for some people, factoring's been their nemesis since grade 10. It was the one thing that your teachers kept telling you in grade 10 and 11 that, oh, this is super important, you have to focus on it. If you're not good at factoring, a lot of things in calculus are not going to go your way. Factoring should be kind of the most used tool in your math toolbox of skills when you're doing calculus. So I'm going to look at this thing and I'm going to factor it. I'm going to factor out 2x plus 3 to the negative 1/2. And you might be thinking, why am I doing that? Well, you'll see in a sec. You'll see why this is a good move. I'm going to factor out 2x plus 3 to the negative 1/2 from this expression on top. I'll leave the bottom alone for now. It's 2x plus 3. And okay, so when you factor something out of itself, it becomes a 1. So this thing becomes a 1 and you just have minus x here. But what does this become when I factor this out of it? Okay, let's just use a piece of scrap paper here. We'll use this piece of paper that I put my answer on here. Let's just use some scrap paper. If you have x to the 5 and you factor out x to the 3, what's left behind is, of course, x to the 2, because these 2 things have to add to make this. Or another way to think about it is, I know this is a 2 because it's 5 minus 3. So if I have something to the power of 1/2 and I factor out x to the negative 1/2 from it, what goes in that blank? Well, what goes in that blank is going to be a 1/2 minus negative 1/2. See now why I chose to do it that way? That's the same as saying a 1/2 plus a 1/2, which is 1. So when I factor negative a 1/2 out of a 1/2, I get that. And of course, the power of 1 doesn't mean anything. So now you're probably looking at it going, oh, I see why he did it that way now. So this is 2x plus 3 to the negative 1/2. And then this exponent means nothing, so I can just go, that's 2x plus 3 minus x, which is 1x plus 3. And then, since this is a negative power, that makes it a reciprocal. So f prime of x is actually going to be 1 over 2x plus 3 to the 1/2 times x plus 3 all over 2x plus 3. And I know you're thinking that looks even uglier than it did a minute ago, but take a look. I can do top times top here. Remember this, I can think of this as over 1, right? So this is top times top, so that's x plus 3 over this. And then instead of dividing by this, I'll multiply it by the reciprocal. So this is going to be x plus 3 over 2x plus 3 to the 1/2 times the reciprocal of this denominator. And then from there, you can see what's going to happen. This, of course, has an exponent of 1. When you multiply together 2 things with the same base, you add their exponents. 1 plus a 1/2 is 3/2. So top times top, that's x plus 3. Bottom times bottom, that is actually 2x plus 3 to the 3/2. And that's the answer that they had in the back. So notice that the calculus was actually the easier part of this. It was the factoring and the simplification that were actually kind of tricky. Now, I did promise I'd do this more than one way. So when I got to there, this is something, again, that one of the students who asked me about this question kind of got stuck at and didn't know what to do with it. So they said, well, I knew that the question had radicals in it, and usually if the question has radicals, they want the answer in radicals. So I changed it to radicals, and it didn't look any better, and it certainly didn't look like this answer. So what can we do? Well, notice that at this point, first of all, do you see what this person did? They just left this as the power of a half, which means it's a square root. But this, of course, is a negative, making it a reciprocal, and then square rooted it. And if you get to here, you know what you can do is you can actually times top and bottom of this expression by root 2x minus 3. In other words, find a common denominator, which happens to be root 2x minus 3. So if you do that, remember that 2x minus 3 square rooted and then times itself will be just 2x minus 3. And now I have that as a common denominator. And then from there, again, this bracket doesn't really mean anything. 2x minus 3 minus x is x minus 3. And I have this denominator all over this denominator. And then once again, instead of having a compound fraction, is what you call that thing, you would think of it as divide by this is the same as timesing by its reciprocal. And I think I'd switch this back to a rational exponent because I'm about to combine it with something. And now notice this is the same last step I had in the other solution, right? This is a power of 1 plus a half is 2x minus 3 to the 3 halves. So there we go. So that's how I would do 6e, and that's how I get that rather ugly looking, or actually much simpler looking answer, but they leave a fractional exponent in it. I think the rule for your textbook, and different textbooks do this differently, the rule for your textbook is if it's just a simple square root or a simple cube root, they'll switch to a radical. But as soon as you have an exponent that has a numerator that isn't 1 and a denominator, I think they'll leave it as a rational exponent. I think that's the way they do it most of the time, if not all of the time. Feel free to look through the answers in the textbook and let me know if I'm wrong about that. But anyway, that's how I did 6e. Okay, I promised you one more. Let's look at number 4. I had 3 different people ask me about number 4. And while I was fighting with all kinds of technical issues on YouTube the other day, I tried to do it for a student, and I think I goofed it up 3 times in a row. So let's see if I can do it once without goofing it up. That would be nice. Okay, so just get organized here. Let me go back to where I goofed it up the other day. There we go. Okay, so first of all, I had one student who asked me about this, just didn't know what it was asking. What it's basically asking you to do is it's kind of asking you to find if this is my function and this thing here goes into where r is, well, that means that actually if I were to write it out in full, it would look like this, and I want the derivative of this when, and then find the value when t is 1. So basically I want f of x or f of 1, if you like, if you want to call this f of x instead of y. And again, I'll do this a couple of ways. In fact, I'll do it 3 different, I'll play with it 3 different ways to show you that they all work. Okay, first of all, I like the chain rule. I sometimes like working with it using Leibniz notation because the Leibniz notation kind of helps me see kind of a strategy to what I'm doing. I would like the derivative of function y with respect to t, but I don't have a t in here, I have an r. R is its own function in terms of t. So what I really want is I want dy of dt, and that's going to equal the derivative of y with respect to r times the derivative of r with respect to t. Remember, that is the chain rule written in Leibniz notation. So let's actually find what this is. So this thing is going to equal that. So let's start with what's dy dr. Well, that's just simple chain rule. Remember, I can write this as 1 plus r squared to the 1/2, right? So that means that I'm going to have, if I'm going to find the derivative of this with respect to r, the exponent becomes a coefficient, and then you leave the bracket alone, but you put -1 from the exponent, and then you times it by the derivative of r with respect to t. So this thing, now I need the derivative of this with respect to t. Well, that's a quotient, so I'm going to have to use the quotient rule on that. So this is going to get kind of big. That's going to be, all right, so quotient rule is the denominator times the derivative of the numerator, which is just 1, minus the numerator times the derivative of the denominator, which is just 2, all over the denominator squared. And there we have it. That's basically it. Now, all I actually have to do to get an answer here, because remember, I wasn't being asked to just find the derivative and simplify it. I was being asked to find the derivative at a specific point when t is 1. So really, all I have to do now is replace r here with the t expression, or the t function. And then I can just evaluate. And that's actually what I did. And like I said, I goofed that up twice. So, well, it doesn't say much for my arithmetic skills. Sometimes you have good days, sometimes you got bad days. And sometimes you forget which kind of brackets you should be writing. If you're putting brackets inside of brackets, you should always alternate between square and curved. And there we go. And then, okay, now I will tidy this up a little. I don't feel like putting ones, again, my arithmetic fails me more often than my algebra does. So I'm going to actually just simplify this algebraically, right? This is 2t plus 1 minus t, right? So that's good, or actually, sorry, minus 2t. So that's going to be t plus 1, and then let's see, what can I do with that? Yeah, that's going to be 2 times, oh, hang on a sec. Oh, wait, see? Look at that, I goofed it up again. Look at that. I forgot something. Okay, see if you can see it. What did I miss? I missed something right in here. What did I miss? Right, dy by dr, when you're using the chain rule, means that there should be a 2r in here. I'm going to put it over here. Do you get why the 2r? Because it's this exponent becomes the coefficient times what's inside the bracket to the power minus 1 times the derivative inside the bracket. I forgot the derivative inside the bracket, which is 2r. So there's another 2r here. So I'll just put it back here. So that's going to be times 2 times r, so times 2. I guess I'll just put that like that, and then times r. And r, what was r again? R is t plus 1 over 2t plus 1. There we go. Now, let me simplify this bracket. Okay, so 2t minus t is just 1t. 1 minus 2 is going to be minus, wait a minute, that's going to be minus 1, right? Oh, hang on, it's 2t minus 2t. Oh, hang on, the t's go away. Isn't that nice? So this is a minus 1, right? 2t minus 2t is nothing, and maybe I should be doing this in 2 steps. 1 minus 2 is negative 1. Yeah, okay, it's negative 1. And then the bottom is still just, I'll just go 2t plus 1 squared. There we go. All right, so what can I do with this mess? All of that, let's simplify it a little bit more. Those 2's cancel, so I don't need that. This negative 1 I could just put as a negative in front of the whole thing. And this denominator times this denominator is just basically 2t plus 1 cubed. So I'm going to leave this bracket alone. And then I'm just going to combine this into t plus 1 all over, and that'll be 2t plus 1 cubed. There. Phew. That, I think, is the right expression. I'll know in a sec because I'm going to plug my t equals 1 into it. And the reason why in that number 6 I just did, I wasn't plugging anything in, so I wanted it to be a simplified answer. I was looking to get the same answer that I had in the back of the textbook. Here, the only answer in the back of the textbook is just an evaluated number. So it doesn't really matter where I stop my algebra and start evaluating. So I might as well stop here. So I'm going to go, okay, so that's t is 1, so that's 1 plus 1, which is 2, over 3. And then that whole bracket's being squared, and then this is being taken to the negative 1/2. Then this bracket is going to be 1 plus 1 is 2, and this is 2 plus 1 is 3 cubed, which is 27. And there we go. So that's going to equal negative, and then let's see, 4 over 9 plus 1 is 13 over 9, because 1 is 9 over 9, right? And that's to the negative 1/2. And this is 2 over 27. Okay, what does a negative 1/2 power do to a fraction? Well, it's going to, the negative reciprocals it, and the 1/2 square roots it. So it's the negative square root of 9/13 times 2 over 27. And I know the square root of 9 is 3. I don't know the square root of 13. And that's 2 times 27. 3 goes into 27 9 times. And yep, I did have the right expression because that was the answer from the back. I remember it from yesterday. So that is how I did this. And notice I even kind of forgot one term here, and I've been doing this stuff a long time, but it's really easy. You got to be really easy to forget something. You got to be very careful. So, is there an easier way to do this? Well, not really, but I did want to talk about some sort of alternate strategies here. Let's say I got to here, and instead of leaving this as r, what if instead of leaving this as r and using chain rule there, what if I played with the whole thing and did it like that? So yeah, so let's see if I can do it that way. Actually, I think this way is going to be much more work. So let's see. I think I'm going to be right about that being much more work. Well, we'll find out in a sec. Okay, so step 1, rather than play with it like this, I am going to get a common denominator here. So the common denominator is 2t plus 1 squared. Okay, so there we go. Common denominator done. And then I'm going to expand that and collect like terms. Okay, so let's see if I can do this without goofing this up. Let's see, that's 4t squared plus 4t plus 1 plus t squared. So 4t squared plus t squared is 5t squared. This has a 4t term, that has a 2t term, so that's 6t. And this has a 1, this has a 1, so that's plus 2. All over 2t plus 1 squared. Okay, now notice that when you square root a fraction, you can square root the top and bottom separately. So if I square root the bottom, I can get just 2t plus 1. The square root cancels that square. So I am basically looking at this. 5t squared plus 6t plus 2 all over 2t plus 1. Let's get a sharper pencil. Actually, I guess I'll have to sharpen a pencil. So let's look at that for a second. Now, keep in mind, I haven't even started doing calculus yet, right? This is still just y. I haven't even started looking for y primed, which is why I kind of did the other strategy first. I like getting into the calculus as soon as I can. But this should get me the same answer, but I think it's going to be more work. I now, if I'm about to start doing calculus, I need to look at this as a rational exponent instead of a radical. And there, that's my y expression that I'm going to actually start using my calculus on. So I'm going to now use the quotient rule. So the quotient rule says it's the denominator times the derivative of the numerator. Here's where chain rule comes in. So let's not goof up chain rule this time. It's 1/2 times the thing inside the bracket to 1 minus that exponent times the derivative inside the bracket, which would be 10t plus 6 minus, okay, so that's the first part of the quotient rule. The numerator, I'm going to run out of room, times the derivative of the denominator. Thank goodness the denominator is pretty easy to find the derivative of. All over the denominator squared. Yeah, see, this is why the chain rule was easier to use in the first step and then simplify later, because boy, that's nasty, doing the simplification first and then the chain rule. But I am undaunted. This should still work. Okay, here's what I'm going to do. This thing here is, again, a negative exponent, which makes it a reciprocal, which means it can go down to the denominator. So this is actually 2t plus 1 times a half times 10t plus 6 all over 5t squared plus 6t plus 2 to the 1/2. Get it? This thing just became a denominator, minus 5t squared plus 6t plus 2 to the positive 1/2 times 2. Oh, that does, well, I could just say all over 1, I guess. That'd be good. All over 2t squared plus 1. Oh, sorry, there's no squared in there. 2t plus 1 squared. All right, next. What can I do with that mess? Well, I think I'm going to get a common denominator here. So the common denominator is just this, 5t squared plus 6t plus 2 to the power of a half. So I'm going to times top and bottom here by that denominator. That's going to, and again, that's actually going to make my life fairly easy. I'm also going to tidy this up. How about I take a half times both of those things, which gets rid of the half, and just gives me 5t plus 3. Notice how much, I mean, really, let's stop and just take a thought here. Notice the calculus is done, and again, what am I doing? I'm doing grade 11 algebra. If you weren't really good at all of the grade 9, 10, and 11 algebra skills, this course is so far beyond you, you might as well say, hey, guess what? Calculus ain't for me. Eventually, your skills got to be there, you know? Anyway, speaking of skills being there, I shouldn't stop in the middle of these and chat because now I've lost my train of thought. And then, okay, basically, since I times top and bottom by the exponent of a half, well, that means I add the exponents. A half plus a half is 1, so that's just an exponent of 1, all over 5t squared plus 6t plus 2 to the 1/2 times 1 over 2t plus 1 squared. Okay, so there we go. Now what? Well, I think I can expand that. And I get 2t plus, actually I'll expand them both. Let's do that. Let's expand them both. So if I expand them both, this is 10t squared plus 11t plus 3. And I'll expand and distribute that negative at the same time. So that's minus 10t squared minus 12t minus 4 all over 5t squared plus 6t plus 2 to the power of a half times 1 over 2t plus 1 squared. Boy, it'd be nice if I could cancel that with something up there, but I don't think it does. This is nice though, those go away, and 11t's minus 12t's is negative 1t, 3 minus 4 is negative 1. Instead of negative t minus 1, why don't I just put the negative out there and say that it's t plus 1. And yeah, and that's it. I have a denominator that has a power, and I have a denominator that has a radical. And that's about as simple as that gets. I don't think I could simplify that much more than that. And just for fun, remember, the whole point of this was we were going to plug in t as 1 when we're done. So let's see. If I plug in t as 1, I get the negative of 1 plus 1 is 2. And on the bottom, that's 2 plus 1 is 3 squared is 9. And that's 5 plus 6 plus 2 is 13. And that's what we got last time. So this is the answer I would have wanted had the question actually said, can you find the derivative and then simplify it? That's about as simple as I'd want it. There might be people going, wouldn't I rationalize the denominator? I could, and then this would be up there, and then there'd be a factor of this down there. But I don't know. I think your textbook doesn't bother rationalizing denominators when the denominator that has the radical has a radical that's more than just a constant. So that's pretty much it. Now, going back to what I had a minute ago, when I was doing it this way, when I did the chain rule first, and then I just got a big ugly piece of algebra, and then I plugged in the numbers, I could have, when I was at this step here, I could have kept playing with this before I plugged in the numbers. So alternative strategy, again, if you don't feel like putting a 1 in this much stuff, you can simplify it here too. Now you might be going, well, 1's not hard to work with. Why wouldn't I do it kind of the easier way? Well, good question. What if instead of this being a 1, what if I had to plug in something like, I don't know, a radical, like root 2 or 0.574 or something not so easy to work with as 1? Then it would be in my best interest to make this as simple as I could. So again, let me get to where I was. I was here. I was right at this step here. I'll just copy it off my other work and try really hard not to mess this up. This is where I plugged in numbers, right? Basically right here. Well, actually, this is the step after, right? I plugged in numbers, I got to here, and then I plugged in 1s. I got to here and I plugged in 1s. What if instead I found a common denominator for that and kept on simplifying? So that's what I'm going to do. So there's the common denominator part, and then I'm going to just keep on simplifying. 2t plus 1. Oh, I shouldn't put that as one bracket because they have different powers. This one has an exponent of 1 on top, and this one has an exponent of 3. There. So let's keep simplifying from here and see what happens. Okay, so if I expand that out, well, I've already seen what happens when I expand that because the other solution had that too. That's going to be 4t squared plus 1t squared is 5t squared. 4t plus 2t is 6t, and 1 plus 1 is 2. And all of that over 2t plus 1 squared all to the negative 1/2 times t plus 1 over 2t plus 1 cubed. Okay, so now what can I do with this? Well, again, a negative exponent on a fraction will give it a reciprocal, and squaring or square rooting power of a half to a 2 will actually cancel. So the numerator is this, and the denominator, don't forget there's a negative out front, and the denominator is this. All to the power of a half. And over here I have t plus 1 over 2t plus 1 cubed. This cancels that down to a squared, and that gets me to the same answer I got the other way. That's 2t plus 1 squared times 5t squared plus 6t plus 2 to the power of a half. Notice, even if I needed to get this sort of simplified answer that I got last time and then plug the number in, notice it was still easier to go through using chain rule first. Then when I got to here, I did some simplificational algebra. Actually plugging in the original function and then using quotient rule then chain rule was by far the least effective of my 3 strategies. Certainly the most work, the most places that I could goof it up and lose a negative or something. So, moral of the story is, try to use the chain rule as soon as you can. If you have to simplify, look for factoring to help you simplify. And if all you're doing is plugging in a number and getting just, a final solution, like a final just numerical solution, you can pretty much just use the chain rule and then stop with all the simplifying, just plug in your number. But if the number is kind of ugly to work with, feel free to use your algebra to simplify it first. So there we go. I don't know who's going to go through all these lessons. Feel free to watch it go back and review it and see if there's places in your work that you can kind of find your mistakes in these. All right, thanks for watching, whoever watched. Bye-bye.